All right, guys. I recently calculated the circumference of the Earth using an experiment that was first done by Eratosthenes over 2,000 years ago. I'll show you how he did his experiment, how I did my experiment, and I'll give you the results. So Eratosthenes, right off the bat, he was the father of geography. He made maps. He was like one of the first big map makers back then, and he calculated the circumference of the Earth back in 240 BC. So let's go over some basic information. So the equator is a latitudinal line, and it runs through the center of the Earth. And the Tropic of Cancer and the Tropic of Capricorn are also latitudinal lines, but what they mark is the furthest north and the furthest south that the sun will get directly overhead in a given year. They mark the summer and winter solstices. And to show you kind of a diagram of how that works, if we have the sun directly over the Tropic of Cancer at the summer solstice, as the Earth rotates around the sun will travel down latitudinal lines till it crosses the equator at the equinoxes, and then it'll go all the way to the Tropic of Capricorn at the winter solstice, and then it will come back up latitudinal lines till it gets back to the Tropic of Cancer, and that would be a full rotation. To get into one more little bit of information, okay, a circle equals 360 degrees. We all know this. But if we have a portion of a circle, then let's say we have a portion of a circle that is 90 degrees, and that portion of the circumference is 25 feet. So if we have that portion of the circle, we could plug it in this proportioning equation to get the full circumference. So if we have 90 degrees over 25 feet being the portion, equaling 360 degrees over the circumference, that will give you the total circumference of the circle. And whenever you solve for circumference, you get a circumference of 100 feet. So we'll come back to that equation in a little bit. So what happened with Eratosthenes is he noticed that in Cyan, while looking down a well, that the sun was shining directly back up at him. And during the summer solstice, he noticed this. So he concluded that during the summer solstice in Cyan, the sun is directly overhead. So what he did was he said, if I know that the sun is directly overhead in Cyan during the summer solstice, then let's go somewhere north and measure the angle of the shadow casted by the sun, get that angle, and do some calculating. So let's show you how this works. So Alexandria was his second spot that he got a shadow measurement during the summer solstice of another year. So if we have Cyan with the sun directly overhead, and then we have Alexandria with the and have the shadow angle, we can know that the angle that the sun is offset in the sky, which is equivalent to the angle between Cyan and Alexandria. And if we have that angle, and then we have that distance between Alexandria and Cyan, we can go back to our proportioning equation and calculate the full circumference of the Earth. So let's show you how that works. So Eratosthenes measured that Cyan and Alexandria were about 5,000 stadia apart, which converted into miles is about 489.95 miles. He also measured that the shadow angle that he measured in Alexandria was 1/50th of a circle, which equals 7.2 degrees. So if we plug that into the proportioning equation, we get 7.2 degrees of a circle equals 489.95 feet, which equals 360 degrees of a circle over total circumference. Solve for total circumference, you have 24,497.5 miles. That's what Eratosthenes calculated, and compared to the what Google says of 24,859.73 miles, the accuracy is 98.54%, which is incredibly accurate for his time. Truly astonishing. So what I did to do a similar experiment, I chose two places that were directly on longitudinal lines, north-south, and took two separate shadow measurements. I'll get more into the equation a little bit later, but so my first location measure site was Earle, Arkansas, and my second site was Hammond, Louisiana. My first site was right off of an interstate and an off-ramp right here. And then my second site was in the back, in the parking lot behind a Hobby Lobby. So I did some checkpoints just to get, just to check Google's distances to see if we were, pretty close to similar. So my first checkpoint was a gas station in Hammond, and I got my odometer reading at this stop, which was 195,101 miles. And then I drove up to Memphis, and I stopped at the Methodist University Hospital, got a odometer reading of 195,431 miles. That gives you a distance between the two checkpoints of 330 miles, according to my odometer reading. And whenever you compare that to what Google said using their measuring tool, which is what I did was I measured along the route that I drove with this light yellow line, that gives you 136.17 miles, a difference of 6 miles. Accuracy level, I think it would be 98.2% accuracy. So pretty accurate, not perfect, but we know we're in the ballpark with what Google's saying the distance is, at least compared to my car's odometer reading. So not a perfect check, but it's a check nonetheless. I'll show you how I am measuring these angles of the sun in the sky. So what I made is basically it's like a shadow caster with a shadow board. The vertical piece is called a gnomon. Then I made a board with legs on it, adjustable legs to get it level. And so what's happening is we know the height of my gnomon, the vertical piece, and then we measure the length of the shadow, and then we can plug in the equation tangent angle equals opposite side over adjacent side. We're solving for the angle. Angle equals tangent -1, shadow over gnomon, the vertical object. And that gives you the angle offset of the sun in the sky. And then how it works is I'm going to get my angle of the sun in the sky at the two sites, and then the difference between these two angles, we're going to call it the delta angle. And that's basically the angular difference between site 1 and site 2. And if we have the distance between site 1 and site 2, we can go back and use it just like Eratosthenes and plug it into our proportioning equation. So at the first site, I got a measurement of 12 and 5/16 inches. You can convert, which converted to feet is 1.026042 feet. When you plug that into the tangent angle solving equation, you get an angle of 11.59658 degrees. And that is, again, in Earl, Arkansas. And then we go to our second site, and we measure a shadow distance of 7.25 feet. 7.25 inches, which equals 0.6041667 feet. Again, when we plug that into the triangle equation, we get an angle of 6.889838 degrees. So now that we have these two angles, we subtract from one another, giving you a delta angle of 4.706747 degrees. So now we have our delta angle, and then we have our distance based on what Google gave us, a straight line distance. You plug that in, 4.706747 degrees over 319.04 miles equals 360 degrees over circumference. When you solve for a circumference, you get 24,402.08 miles. So in conclusion, my accuracy level compared to Google is 98.16% accuracy compared to Eratosthenes, which was 98.54, which is incredibly impressive that he was able to get that accurate using his methods over 2,000 years ago. All right, well, there you have it. That is my experiment and Eratosthenes' experiment. It's pretty cool that we got within 100 miles in our calculations of the circumference of the Earth. Little butthurt that he beat me, but it was a pretty cool experience sharing in some history of some prominent science that was conducted so long ago, and very impressive that Eratosthenes was able to be so accurate despite the limited technology of the time. So there you have it. Hope you learned something. And yeah.